summary. The major function of a structure is to transfer loads, and the main sources of these loads have now been identified. Whilst each load or set of loads can be considered to act independently, buildings are usually loaded by combinations of the various loads. As the building must carry any combination, it is usual to consider a range of combinations called load cases. The only load case that will always be present is the natural gravity load. That is the effect of gravity on the building construction, and to this load must be added all other loads. All the other loads that have been identified may or may not be acting at any particular time. Therefore, an almost endless variety of load combinations may act. For example, load case 1. Natural gravity load plus useful gravity load on all floors. Load case 2. Natural gravity load plus wind load in a particular direction. Load case 3. Natural gravity load plus useful gravity load on some floors plus natural temperature load. However, the purpose of considering these different load cases is not to find as many load cases as possible, but to ensure that the building structure will safely carry all possible load cases. This apparently contradictory statement means that only the load cases that cause the biggest effect on the structure need to be considered. In other words, only the worst load case is of interest. For buildings, it is usual to consider natural gravity load plus maximum useful gravity load, natural gravity load plus wind load in direction 1, natural gravity load plus wind load at right angles to direction 1. It is unusual to have to consider loads due to earth or water pressure, ground movement, temperature or accident. But for particular types of building or sites, these may have to be considered, and incorporated into the load cases. For example, for a 2-story factory building, the following loads would be considered for the structural design. The ground floor often bears directly onto the ground and does not load the structure. The natural gravity plus maximum useful gravity loads usually, but not always, give the worst vertical load. The combination of natural gravity load and the maximum wind loads usually gives the worst horizontal load. It may seem surprising that only 2 directions are chosen for the wind, because, after all, wind blows in any direction. So the maximum wind load, which has been decided, can act in any direction. But if the building structure is strong enough to carry the maximum wind load separately in 2 perpendicular directions, then all other wind loads can be considered to be smaller proportions of the maximum loads. The same principle of load combinations applies to all buildings. In the same way that people stand on a floor and usually don't fall through, buildings also have to stand on something strong like foundations. But what is the floor doing to stop people from falling through? What it is doing is to provide a reaction force or a reaction load. The idea of reactions is due to Isaac Newton, who in 1687 stated 3 fundamental laws, which together with his discovery of gravity, provided the basis of what has come to be known as Newtonian mechanics. These were used extensively by scientists in their pursuit of knowledge about the natural world. They formed the backbone of physics and still provide the backbone of structural engineering thought. It was only at the beginning of the 20th century that Albert Einstein postulated a system of mechanics that were non-Newtonian. This system came to be known as relativity, which is used for calculations about the universe. Fortunately, structural engineers can still use Newtonian mechanics for building structures on the Earth. One of Newton's 3 laws states, "To every action there is always an equal and opposite reaction." So when a person stands on a floor, the weight of the person pushes down on the floor with a force equal to their body weight. For equilibrium, the floor must push back with an equal and opposite force. An understanding of this statement is fundamental for an understanding of how building structures carry loads. Whilst it is true that the load and the reaction have to act at the point of the application of the load, a structure transfers the load to another point. Returning to the example of the plank bridge, the reaction to the person's weight is in the structure, and the structure transfers this reaction to the banks. Because of Newton's law, the numerical sum of the loads and the reactions must be equal. For vertical equilibrium of the 2-span beam, P1 plus P2 plus P3 plus P4 equals R1 plus R2 plus R3. When loads are acting horizontally, a reaction is required for equilibrium. It is to upset this equilibrium that tug-of-war contests are held. Here it is unclear which is the load and which is the reaction. This is why the applied load and the reaction load should be thought of as a balanced system of loads. Here the pull of the team is the applied load and the tree provides the reaction load. Not only are there vertical and horizontal reactions, there are also moment reactions. What is a moment? A moment is a force times a distance. Moments abound in structural engineering, but the concept of a moment is often found hard to understand. However, it is because of moments that things can be weighed or people can enjoy see-saws. The fun in see-sawing can only be enjoyed if the people are of equal weight and sit at an equal distance from the support. This is because they are in moment equilibrium. In other words, the left-hand person causes an anti-clockwise moment and the right-hand person causes a clockwise moment about the central support. Because both people are of equal weight and are sitting at equal distances from the support, the anti-clockwise and clockwise moments are equal in magnitude but opposite in direction and so are in moment equilibrium. By pushing from the ground, this equilibrium is upset and the people see-saw. The same principle can be used for weighing scales, this time to find the unknown weight of some goods. To balance the scales, the moments must be equal. As the distances are equal, the weights must equal the weight of the goods. The idea of moment reaction occurs at the support of a cantilever. The person sitting on the end of the cantilevered plank causes a moment at the support force times distance. The fixing of the plank must balance this moment with a moment reaction, otherwise the plank will rotate away from the wall. Moment reactions are also required to prevent flagpoles, fences and signs from being blown over by the wind. In this case, the post is acting as a vertical cantilever from the ground. The wind force acting on the sign at some height distance above the ground causes a moment at ground level, so the post must be dug into the ground to provide a moment reaction. Notice that the moment reaction is in the opposite direction to the moment caused by the wind force times height. Many structures require more than one type of reaction. Using the example of wind blowing on a sign, the support must provide vertical, horizontal and moment reactions. These resist the weight of the sign, the wind load and the wind moment. The idea of moment equilibrium also plays a part in apportioning vertical reactions for spanning structures. Suppose a weightless plank spans between two weighing scales and a person stands at different points along the plank. The person is the load and the reaction forces occur at the supports on the weighing scales. As the person moves from position A to B and then to C, the readings on the scales will vary, giving the values of the reactions for each position. But the fact that the sum of the readings on the scales for each position will equal the weight of the person does not indicate how they are shared. If the person stands in position A, directly over the left-hand weighing scale, it is reasonable to expect this scale to give a reading of 100% of the person's weight, and the right-hand weighing scale to give a reading of 0% of the person's weight. But vertical equilibrium would equally be satisfied by the right-hand scale reading 100% of the person's weight, and the left-hand scale reading 0%. This seems unlikely to be true, but why not? The answer is because only 100% at the left-hand scale gives moment equilibrium. But where are the moments? These are far from obvious, but suppose the left-hand weighing scale was removed. Now the person causes an anti-clockwise moment about the right-hand weighing scale and the plank would hinge about the right-hand end. To prevent this, the left-hand weighing scale provides a reaction that causes a clockwise moment about the right-hand weighing scale. As these two moments must balance, the left-hand reaction must balance the person's weight, as the distance from the right-hand end is the same for the load, and the reaction so. Person's weight times length of plank equals left-hand reaction times length of plank, so the left-hand diagram gives vertical and moment equilibrium whereas the right-hand one gives vertical equilibrium but not moment equilibrium. So every time there are loads on structures there must be reactions vertical, horizontal and moment, and these reactions must balance the loads. In other words, sum of vertical loads equals sum of vertical reactions. Sum of horizontal loads equals sum of horizontal reactions. Moments due to loads equals moments due to reactions. These three statements must be true for all structures, and the understanding of these statements unlocks the door to an understanding of structures. To understand how loads are transferred through complex structures, the concept of load path is used. This is basically a sequence of loads and reactions between structural elements. The important point here is one element's reaction to the next element's load. For the simple example of a beam on two walls, the reactions of the beam cause loads on the walls. The double-headed arrow between the beam and the walls represents the reaction and the load. The upper arrow represents the wall providing a reaction to the beam, and the lower arrow represents the beam causing a load on the wall. A more complicated situation of two beams supported by walls, all sitting on a longer beam. First, what are the loads? These are natural, the self-weight of the beams and walls, and useful, the loads applied to the beams. Loads P1, P2 and P5 are the self-weight of the beams, and P3 and P4 the self-weight of the walls. Loads P6, P7 and P8 are the loads applied to the beams. For vertical equilibrium, all the loads P1 to P8 must be balanced by the reactions of the lowest beam. For the lowest beam, the sum of the reactions equals P1 plus P2 plus P3 plus P4 plus P5 plus P6 plus P7 plus P8. But how do the loads get to the reactions? First, the upper beam. Loads to the upper walls equals P1 plus P6. The upper walls are loaded by the loads on the upper beam plus their self-weight. The tops of the lower walls are loaded by and provide a reaction to the upper walls and the middle beam. So for the lower walls, and the reactions to the lower walls are load from the upper wall plus load from the middle beam plus self-weight of the lower wall. Reaction equals P1 plus P6 plus P3 plus P2 plus P7 plus P4. The lower beam is not only loaded by its self-weight, P5, and the applied load, P8, but also by providing reactions to the lower walls. So for vertical equilibrium of the lower beam, the reactions equals self-weight of the upper beam plus self-weight of the middle beam plus self-weight of the lower beam plus self-weight of the upper walls plus self-weight of the lower walls plus useful load on the upper beam plus useful load on the middle beam plus useful load on the lower beam, which is R1 plus R2 equals P1 plus P2 plus P3 plus P4 plus P5 plus P6 plus P7 plus P8. The load path of load P6 can now be identified. First, the upper beam transfers the load to the upper wall, which transfers it to the lower wall, which transfers it to the lower beam, which transfers it to the supports. And for P2, the self-weight of the middle beam, the load path joins the load from its point of application to the final support point. There are two facts to be considered about load paths. Firstly, all loads must and will have a load path from their point of application to the final support. The structural designer must identify these paths for all loads and all load cases. Secondly, as the function of the structure is to transfer loads, then the load path is the structure for each load. So the answer to the question what is the structure may vary with each load. For the loads P2 and P6, the structures are different. The identification of vertical load paths for most buildings is relatively straightforward. Oddly, it can be quite complex for simple buildings, like houses. Not only do vertical loads need load paths, but so do horizontal loads. These loads are usually caused by wind. How does the signboard resist wind forces? The main wind load is caused by the wind blowing on the actual sign, and only the load path for this load is considered. This means the effect of the wind on the rails and posts is ignored. The actual signboard spans horizontally between the vertical stiffeners, and the stiffeners act as vertically spanning beams, supported by the top and bottom rails. The reactions from the stiffeners become horizontal loads on the top and bottom rails. These rails act as horizontally spanning beams, supported by the vertical end posts. The reactions from the top and bottom rails now cause loads on the vertical posts that act as vertical cantilevers from the ground. For the signboard, the wind load path is the whole structure. But even in simple buildings, the load paths for vertical and horizontal loads are rarely the same. As the load path is the structure, this means there are usually different structures resisting vertical and horizontal loads.